Well, welcome everyone. So this morning I'm going to talk about selecting the next database for your next project. We at Franz sell AI tools, and we sell a list compiler, and for the last 15 years we've been selling drivers to relational databases. Since about 10 years we have an object-oriented database which is completely one with the language that we have, and since the last 4 years we're really into graph databases, or what some people call triple stores. So one of the questions that we get when we talk to customers is, okay, so what database should I use? And some people are really in love with the new technology and they would like to use the newest stuff that we have for every project that they do, but that's usually not a good idea. There are application and use cases where a relational database is absolutely a better choice. There are situations where you want to use an object-oriented database, and there are situations where a relational database, a graph database makes much more sense. So I'll talk about those things this morning. I think that in the audience there might be a few people that don't know what a triple store is. So I'll spend about 3 minutes trying to do the shortest explanation of triple stores in the history. Then I'll go into some applications where customers started out with a relational database but then switched over to using a triple store, not necessarily our triple store. And once I've talked about those use cases, I will go through relational databases, object-oriented databases, and triple stores, talk about the basic technical characterization of those. And then I'll present some criteria for choosing a database. Well, up to this point, I'll try to keep it as impartial as possible. And then in the last part of my talk, I will talk about some things that you can do without triple store that are very hard to do in other triple stores. And then for people that want to hang around, stay around, I will do a demo, show some of our features. Okay, so let's begin. Well, I already told this. We are around for 25 years, self-funded company, and most of our customers are actually in the government and in the industry. So let's start talking about what is a triple store? What are graphs? What are triples? And why do you store them in the triple store? So normally when you create a database, you start by thinking hard about your schemas, and then you will create your database. First create your schemas and then add data to the database. With a triple store, you work almost the opposite way. Here you see part of our Python interface. So what you do, just type create a triple store, and now I have a triple store called seminar.db. And then I can just say about anything I want, about everything. So say I want to add some information about a person, Steve. So I would add a triple. Person 1 is the first name, Steve. Person 1 is an organizer, and person 1 is 52. Those are 3 triples. In the language of the semantic web, person 1 would be the subject, this would be the predicate, and this would be the object. I hope you can see my mouse move here. Okay. So now we've said something about Steve. Now let's say something about myself, about Jans, who's a psychologist and is 50 years. And let's say something about my other colleague here, is Craig, who is a salesperson and is 32. Yes, so now I have 3 objects in my database. And now let's add a one-to-many relationship. Well, in a relational database, you would start a link table in a triple store. You just say person 1 is a colleague of person 2, and person 1 is a colleague of person 3. And given that you can say about everything you want in a triple store, just let's add some weird fact like that person 1 likes the pizza. And now we have a set of about 11 triples here. And these triples together make up a graph. What you see here is a part of our AllegroGraph browser, which shows triples in the form of a graph. And at the end of my talk, I will do some demo and I show multiple views of the same data. But it is a graph, so these things here where my mouse is are the nodes, and then the lines between them are the links, and this is the typical graph. So now let's add some more triples. Yeah, let's add another one-to-many relationship. Say that person 3 is a neighbor of person 1, and person 3 is a neighbor of person 2. Now we have an extended graph where, for example, here we have a new neighbor relationship between person 3 and person 2. And then once the data is in the database, in the triple store, you can do queries. This is something that looks very close to the Sparkle language. By the way, we completely support Sparkle, but this is an alternative internal query language. You could say select every X name and Y name, where X is the colleague of Y, and Y is the neighbor of X, and X is the first name X name, and Y is the first name Y name. And then like a relational database, you get back a table with 2 columns, where everything is just a string based, and you can get a cursor and you can do whatever you want in your programming language. So that's a very, very short introduction to a triple store. So now when do you want to use a triple store? Before I go into use cases, in general I would say when you want to model knowledge and assets, when you have thousands of objects with different feature sets, and every day you add new objects with new features. And then, because this gets so complex, you need some abstraction layers on top of your objects, so you will want to work with views and rules. Although sometimes also the use case is just that you have very regular data, but there's a very big graph in there. And sometimes you get both. So these are the use cases, but now let me give you some examples of these use cases. So I'm going to go into detail a little bit about a project that runs at NASA, a new project that we do together with an organization, geospatial organization in British Columbia. I will talk about MetaWeb, about a project we do with people in Stanford with biological databases, a project we do with Kodak about multimedia metadata, then a project that's going on at Sun about bug and version tracking, and then I'll say a little bit about a project that's running at the DoD. Okay, first NASA. So NASA has this new big project where they want to get a person on Mars. And in order to do that, you need to use all the knowledge in your organization. But all the knowledge in NASA is distributed over I don't know how many places, and information is in spreadsheets, in drawings, in people's heads, in documents, in process descriptions, in software, and what do you have? So what a group in NASA is doing is they are writing ontologies, people not familiar with that, concept descriptions of basically roughly everything, of every asset in NASA. And they've put those descriptions in probably hundreds of distributed databases. And then they have a registry that knows where a particular knowledge is, and they are able then ultimately to say things like, okay, find me a person that knows everything about rubber rings that can stand both extreme heat and extreme cold. Or how long can a particular person stay without oxygen. So I mean, it's the typical, what you want to do is make a very, very advanced semantic search within your organization. And it's a wonderful project that probably could be used in many other enterprises that are very knowledge intensive. Another very, very recent project that we started working on is doing complex computations of the graph in a river network. So if you look here at the left side, you see a nice picture I found on the internet where a typical little river where you have segments. So this would be one segment if you follow my mouse. And on the left and on the right of each segment you have a drainage area, and then each segment has one or more upstreams. Yeah? And so here's a really a somewhat bigger network, and the network that we are working with that is in British Columbia has got about 6 million different river segments. The data is actually very regular, so you have triples in the form of there's a stream of type stream segment where S1 has an upstream S2 and S1 has an upstream S3, but the same S1 also has a left drainage and a right drainage. And for simplicity's sake, we don't represent the whole line. So we just give the beginning and the end of the line. And then what you can do with this data is, say you find a polluted place somewhere downstream. You want to find all the things that could have caused it upstream, or say you have a pollution upstream, you want to find all the downstream places that could be affected. Now, this data is currently in relational databases, but it's just impossible within relational databases to do really efficient graph search, and especially if you want to combine efficient graph search with geospatial capabilities. So that is just one other example of why you want to use a triple store to do some particular complex type of analytics. Then another customer that we have is Kodak, who is storing literally hundreds of millions of pictures of people. They want to be able to add far more advanced services on top of that. For example, create stories out of your picture books. In order to create these stories, you need metadata about pictures. And so what they will have is per picture at least 200 metadata elements. Some of them are device dependent. Some are about the time it was taken, where it was taken. It has this advanced recognition software for faces, so that you know who's in the picture. You will be asked to tell what your relation is to the people in the picture, so there's actually in those pictures also a big social network. And all in all, you get a really interesting semantic web that you can use to create advanced new services. Here is a article. So we'll put this presentation on the web after here. So please take the time to read how Kodak is actually using the semantic web to do personalized story creation. And ultimately, I guess it will wind up on the Kodak website. Okay, then biologists. In general, people in medicine and biology were the first to give up relational database for some particular problem domains. For example, here is a project that runs at Stanford where they want to create a portal for biological databases. And the problem that they are faced with is that they have 111 ontologies of biological things, whether it's genes or pathway expressions or what do you have. And in total, they have almost 500,000 different classes of objects. And you can't even imagine that you would try to describe all these classes and the relationships between these classes in a relational database. Then another great example of where people chose to use a triple store is Freebase. Everyone in the audience is familiar with the Wikipedia, and if you look at the Wikipedia, it looks kind of fairly irregular. But what you have to realize is that the Wikipedia is written by people and for people. It's not really written to be read by computers. So, and just if you look at the Wikipedia, there's, for example, already 12 ways to say that someone is born in a particular place. Yeah, so it's really hard to do reasoning over Wikipedia if you have such a diverse vocabulary. So what the Freebase people have done is they, for example, scraped Wikipedia and then harmonized all the predicates. So in in Freebase, there's only one predicate for born in. So that's one thing they did. The other thing they did is, which I find very interesting, is that they have these concept descriptions, and then every concept will get a unique ID. So Steve Jobs will have a unique UUID in this database. And I can imagine in the future that every web page will have, well, it will have text about people, places, events, but invisible in the HTML, you will have put the UUIDs of the things that you talk about, so that you actually can disambiguate about which Steve Jobs you are talking. There's probably 1,000 Steve Jobs in the United States, probably far more. And by adding a UUID in there, you actually know about the person you're talking about. So I'm really excited about this new service. Now they have their own kind of triple store. So here are some examples of triples that you can find in Freebase. Actually, if you go to Freebase and you hit F8, and at the bottom you will see a kind of a developer screen. And if you go in there, you actually can inspect all the triples for all the things in Freebase. Very fun way to explore what they have in their website. People also do regular things with triple stores. Here's a thing happening at bug tracking, a versioning tracking, a database, many one-to-many, many-to-many relationships. And they could have done it with a relational database, but it's just such a complex schema that they are trying it now with a triple store. And then finally, just last week, I saw this list of Time's best inventions of 2008, and one of them was a Facebook for spies. So the analysts at the intelligence agencies also use a Wikipedia or a wiki to describe things they observed. So they might have observed that a particular person was talking to another particular person at a particular time, probably about a particular topic, and it was observed by another person. And the trouble is, of course, that if you don't have semantics for such a wiki, then it's very hard to combine with the various people, because were people talking about the same person? People might use different labels or predicates to describe stuff, and so they're doing a large project where they add semantics to the wiki, and they will use a triple store beneath all of this. So here are some use cases where, yeah, a relational database wouldn't be the best choice, but you probably use a more flexible technology. So again, I'll just summarize again. You use the use cases for triple stores in what I just showed you. You're modeling knowledge and assets. You've got literally thousands of objects with different feature set. You get new objects and new features every day, and you want to work with rules. Okay, so now, are these databases really different? To some extent, all databases can do the same thing. I mean, if you look at relational databases, OO databases, graph databases, to some extent they are Turing equivalent, although that's something you can't say about databases, because Turing equivalence applies to programming language, but I guess most of you will understand what I mean. So let's go through each technology. So first, relational databases. Sometimes you read articles or you hear people talk about that the relational database is dead. Well, these people are really, really mistaken. I think that even in 50 years, the relational database will be still very, very important in the enterprise for the typical accounting applications. It's a proven technology. Relational databases started out in the 70s at the time where, say, disk space was a scarce resource. So they came up with an extremely efficient table representation for data. And then they have been working for the next 30 years to make the joins for queries as efficient as possible. And the one thing that made SQL an enormous success, or relational databases an enormous success, was that they had a standardized query language where it was just ideal for the enterprise. You can easy to learn the easy queries, easy to find programmers. But of course the problems are, that's why we now see so many new types of databases coming up, is that these databases are inflexible when you change tables on a daily or weekly schedule. And the gets a nightmare if you got too many one-to-many or many-to-many relationships. And I would say that about half the time a DBA is worrying about what to index because particular queries are slow and you just want to get them faster by having new indices. And then one other problem is that if in the Bay Area where we live you want to get a good DBA that can do really complex SQL queries, then $120,000 per year is the least. Okay, so that about relational databases. Then object-oriented databases. Object-oriented databases have the biggest, well, objects are for some people more intuitive because they resemble real-world objects. If you look at all the programming languages that are now in vogue, then you see that they all have gone object, whether it's Python or Java or Ruby or, well, whatever language you talk about. It's all object-oriented. And so there's this weird dependence mismatch between programming languages and the databases. And object-oriented databases take that mismatch away. So it's really easy in object-oriented databases to program your objects and then transparently for you, they get stored for you. And even changing classes is a lot easier in object-oriented databases. The biggest problem that I've seen why object-oriented databases don't really take off is there never was a real good standard for the language. And to some extent, if you want to work with a relational database, roughly the only thing you need is to learn SQL because the company probably can pay for a DBA that takes care of all the installation stuff. So they decouple the installation and dealing and managing the whole database with the people that use it. But object-oriented databases, you really need programmers to make it work, and it turned out to be a lot harder. And then triple stores. The triple stores, you store objects as sets of triples. One-to-many relationships are directly encoded. Everything is indexed, and you don't even have a choice because just everything is indexed, because you never know what you want to ask. And basically, triple stores are designed to make ad hoc queries a lot easier than with SQL. Fortunately, for triple stores, all the data structures are standardized by W3C. I guess most people in the audience will be familiar with RDF, RDFS, and ALL. And the great advantage is that you can take data from one triple store and put the data in another triple store, and it will just all work. And then there's a query language that is standardized, the language Sparkle. And again, the big hope is that like SQL, that will make it a lot easier to get adoption in the marketplace. Now the biggest problem, of course, for triple stores is that it's a new kid on the block. Relational databases are very, very mature right now. They have 30 years of development. Object-oriented databases 10 to 15 years. And triple stores have just been around now for, say, 4 or 5 years. So that's about the 3 technologies. So now you have your new Web 2.0 or even Web 3.0 application, and you need to choose your database. So what are the criteria? How are you going to choose? Well, basically there are, if you just choose your new database, there's both technical reasons and there's business considerations. So let's first look at the technical reasons. I would say that, you're doing your new project and you have to answer the next 4 questions. You have to say, well, do I have to work with, say, hundreds of thousands of objects in one-to-many or many-to-many relations, and it would be fantastic if everything got indexed. Or you ask yourself, do I need pattern matching on my data and recursive graph search? And the third question would be, does my data change all the time? And then finally, is my application maybe too complex, and do I need abstraction, and do I need to work with rules and reasoning? Now, if you say yes to all of those, then you might want to consider new technology. But then on the other hand, you live in a business environment, so one of the things that you think about is, can I find the programmers and database administrators to deal with all these new technologies? Or I already have all these reporting tools, and do I have to change all my reporting tools if I go to this new technology? And finally, will it all work with my existing relational databases? How do I get my information from the old to the new? Yeah? So if you fill this thing in, then, now of course I know that feature comparison charts like this are instrument made by the devil to manipulate other people, but I mean, just work with me here. I'm just trying to sketch a general picture. And so the general picture is, if you say yes to these questions here, then you probably want to have a database like this. But then on the other hand, you have to be realistic. You're working in a business environment, and then relational database score much better here. So you, as the manager, that has to make this decision about what technology to choose next, has a really, really hard choice. I do have to say, by the way, that we are working on a database import tool that will make it a lot easier to go from a relational database to a graph database. So, Steve, are there any questions so far?
People are waiting till the end.
Okay. So one of the things, by the way, this is I gave this talk before a week ago. I really got many times this question about when to choose what type of database. I would be very, very interested to hear from the audience what you guys think. This is an experiment. I'm trying to provoke a little bit, but I hope to make this presentation a lot better and ultimately to write a paper about it, or maybe one of you guys will write a paper about it. But if you disagree with me, please reply to the questionnaire that Steve is going to send out, because yeah, this is for me more an experiment to try to explain it, but you guys might have much better arguments that I have, both to support me or to criticize me. Okay, so now up to here it was slightly impartial. Now we're going to the more partial part, and we'll talk about more our own triple store. So the triple store that we provide is called AllegroGraph. It's a scalable and persistent triple store, so not something that's in memory, but really stored on disk. We load right now the fastest in the industry. We load 1 billion triples in 8 hours on a 4-processor AMD machine, and we also can work on the cloud, where we have loaded now up to 10 billion triples on EC2, and we expect to have, say, early next year to provide AllegroGraph as a software as a service, where we'll just have a web address where you can add triples. So that will be an interesting thing. One of the things that makes AllegroGraph also unique is that we can use federation. So what you can do is you can load on the same machine or different machines, different triple stores all at the same time. And then when you want to start working with queries, we can create an abstract store that is basically nothing but a pointer to the other stores, and then our Prolog and Sparkle and reasoning will all work transparently against the abstract store. So the query engine will know where the triples are. And we made sure they were compliant with all the standards of W3C. Then something that makes if you look at something that makes AllegroGraph really unique is that we provide in our triple store range queries. Nearly all triple stores, and also our first triple store, basically stores triples as pointers into dictionaries. And that means that if you have numeric values in, say, the object of a triple, say you have 100 million people, that you describe 100 million people in your triple store, and each has a particular age, and you want to know everyone between 50 and 70, then it's going to take a while, because you have to go through the dictionary, through every age, and then unmarshal it and look at the value. We have a storage engine where we index everything, but numeric values are stored in a sorted order. So our range queries are just as efficient as relational databases. And given that we have that efficiency, we also can do geospatial primitives in our triple store, and we can reason about time. And at the end of this presentation, I'll go a little bit deeper into that. And then finally, what we saw is that many people actually want to use this for social network analytics. So we provided a whole library on top of the triple store. And then finally, a fairly new development is that we provided a much faster reasoner on top of a triple store. In general, triple stores load the data in bulk, and then what they do is they pre-compute all the types and all their inferences, something what people call materialization, and then they do queries. We don't really believe in that model. What you really want is dynamic triple stores where you can keep adding triples all the time. So what we will have, and this is probably going to come out in January, is the first a completely dynamic real-time triple store where you can load triples in linear time, and queries and reasoning can be done at any point in time during the loading. And we will not pre-compute types, but our queries will be just as fast as the triple stores that materialize the types. And then one particular use case that people use AllegroGraph for, so up till now I talked about a kind of generic triple store with some special features. But one of the things that people really use us for, and that's because our product is mostly used in the government, is they use AllegroGraph as an event database with social network analysis and geospatial and temporal reasoning. So with that database, you can do queries like, find all the meetings that happened in November within 5 miles of Berkeley that was attended by the most important person in Janss's friends and friends of friends. And below that, you see the query in our query language. So currently, this is Prolog. It won't take long, and then we'll also be able to provide the same query in Sparkle. And what you see in this query that we do two things. The first two classes are social network analysis, and then we do a basic query lookup. And then we do a little bit of RDF reasoning because we reason about a type, and then we have a temporal and a spatial class. We can mix that all in the same query language. Now, I was talking about that this works on top of events, so we provide a very simple event ontology. Basically, events are things that have a type. It could be a meeting, a communication event, a financial transaction, and what do you have? A list of actors. Sometimes it's only one, sometimes it could be a group. Events usually happen somewhere. Events always happen in time. And then, of course, there's a lot of other information that describes an event, depending on the type. And then I want to go a little bit deeper into the 3 capabilities that I talked about earlier: social network analytics, geospatial, and temporal. So what our social network analysis library does is basically answer 4 different types of questions. With our software, if you have represented people in the database or companies, you can say how far is this company or this person from the other person, and also how strong is that relationship. Then if you have a particular person, then we can compute the groups that a particular person is in. So we can do both ego groups, just friends and friends of friends, or completely connected groups, which are cliques. So, for example, I hope people understand what a fully connected graph is. So, for example, I have a family clique where everyone in the family knows each other. I have a tennis clique with my friends. I have a work clique, and I have a, well, this is the typical type of cliques that marketeers are interested in. And if you have a group, and you have a particular person in that group, then you can compute how important a particular person is in the group. There's various statistics for that. And then finally, if you have a group, we can compute how cohesive the group is and whether the group has a leader or not. So that's about a social network analysis. We also provide geospatial capabilities. We don't have, like Oracle, 500 functions in our libraries to do all the wonderful things with polygons, but the thing that we do really well is you can represent where things happen, and we do the thing that every geospatial database should do as fast as possible, and that is find all the events of things in a bounding box or radius of m miles or centimeters around a particular order place. And then finally, a lot of things that if you describe events in your database, then there's always a start time and an end time. And we use James Allen's reasoning, temporal logic, where you can look at intervals in every possible way. Two intervals are can be related to each other, and we wrote some kind of a usability layer on top of a triple store, so that's very easy to say that one particular interval was before another interval, whether two intervals meet, etc., etc. So it makes it very easy in the same query language to say things about the time an event happened, where it happened, who was there when it happened. And I think that was everything that I wanted to show in this particular PowerPoint presentation. Oh no, the last slide is about what I'm going to do now is, for the people that want to hang around, is give a little demo of some of the features in our triple store. I'm doing that in Lisp, but you can go to our website, www.franz.com, and you can click on Learning Center, and then you will find roughly 100 Java examples, because you also can do everything you can do in Lisp, you can do in Java, and actually now also in Python, or with a REST interface. Okay, so given that this is the end of the PowerPoint presentation, I would like to know if there are any questions now, or do we want to wait till later?
So far, there's no questions.
Okay. Then, okay, let's do a demo. So what you see here is our IDE. And let me close all the triple stores that I've opened. Okay, so first let me show you that I just created a triple store. So I take a triple store. I made a triple store seminar DB. I register a namespace because everything is in RDF, but I don't want to type these horrible long namespaces. So I just say whenever I see the word, when I see the symbol O, actually I mean this thing here. Now let's add some triples. I say person 1 is first name Steve, and he's an organizer, and he's 52. And Jans is the psychologist, and he's 50. So every time you hit click, I'm actually evaluating it. And then Craig is the salesperson, he's 33. And person 1 is a colleague of person 2 and person 3. And person 1 likes pizza. And then I can show the store. Okay, so here you see the graph that we have at this point in time. I can center the graph. I can click on a particular person. And what you will see here is that we also have just a normal kind of a database view where we have a person 1 here with an age. He's a colleague of, a first name, likes, and type. And we even could do a Sparkle query here where we will get the results back, but let's not do it now. Go back to the graph. I can add some more triples. Person 1. Person 3 is a neighbor of person 1, and person 3 is a neighbor of person 2. And then show the store. Now we see this new relationship here. So neighbor of is now getting a little bit thicker. And so roughly that is the graph. So now you see how simple it is to add triples and look at the results. Let's do a little bit of geospatial work. So one of the things that you can find on the web for geospatial database is the GeoNames database, which is, you can find at geonames.org. It has nearly 7 million points of interest on Earth. Each point is roughly about 10 triples. And for this demo, I made a selection of populated places in the United States. So I opened a database with that stuff on my machine here. Then please don't watch this. But let's look at one of these pictures. So here I have one element out of this database, which is the ID 5374671. I could look at all the predicates for this thing. I select all, say OK. So now I could look at this particular place. It's Moraga. The elevation is 152. This is the longitude. So, well, let's actually do it this way. So this place has an administration code, which is California. 13 is the code for California. The name is in the U.S., 152 meters high. Populated area is what it means here, latitude and longitude, and and everything else. So that's what in the database. So then I can select places. I can say, okay, find every X that has the ASCII name Berkeley. And you see here on the left 3 places, because Berkeley happens actually 3 times. So let's find only the Berkeley that has the administration code CA. So you have to read it like this: find every X where X is the ASCII name Berkeley and X is the admin code California, and then print the subject. So now we find all the triples about Berkeley. Now personally, I live in a city called Moraga, and Moraga is at longitude latitude minus 122.37. Berkeley is very close. Look here, it's got only almost the same coordinates. And what is the distance between the two? Well, I've got Moraga, Berkeley. So here I find that it's 8.2 miles from each other. And I can also say, for example, find all the places around Moraga within 10 miles. So I say find every X that's the name Moraga that is within 10 miles, where Y is within 10 miles of X, and where Y has the name. And now I get the names. Now, of course, it's much better if I show that directly on a Google map. It's going to take always a little bit. There's much more I could do with geospatial, but when we're talking about databases, the final little demo I'm going to give is about social. So I close all my triple stores. I open a database which I always call a database of friendship and love, which I actually scraped partly from Facebook. And in the database, you have relationships between people. Well, let me just show you some. So this person, 100 for example, and look at this person. We figured out whether person 1000, we made it an anonymous database. 8 with some other people. He was intimate with only 3 people. He kissed with a slightly larger group of people. Everyone that he links to is, of course, a nose relationship. He went to the movie with the people, etc., etc. So this is the database. So what I usually demonstrate then is, if I go back to the graph view, let me file, uncache it, and let me get rid of the left side, and then let me get some people here. Say person 0, and let me get someone else. Person 999. And now I want to know whether I can find a path from person 0 to person 999. And I only want to follow the intimate list and the kicked with links. Now I can say, okay, look at the links here. There's no link yet between the two. Let me look here. And I already found that person 1 was kissed with this person here, who was intimate with this person, who kissed with this person. If I do this. Now I don't yet have a circle of love where you get back to yourself again, so let's try that. Let's go back here. Add some more relationships. Finally we have one circle of love here where this person had a relationship with this person. So that was just some fun stuff that we do with our database, and I would say that now it's time for questions.